Hello, my name is Jeffrey Chen, and I'm here to introduce Eciton, a very low-power, long short-term memory neural network accelerator for predictive maintenance at the edge. In our modern world, monitoring our surroundings provides an abundance of information that can be used. Cyber-physical systems integrate sensing, computing, and networking into infrastructure and physical objects. End-node devices transmit or process information and relay it to a central processing system for further evaluation. Applications include personal health monitoring, such as fall detection, geofencing, and drone routing. In many instances, cyber-physical end-node devices are in remote environments with intermittent and limited sources of power. Some of the ways that cyber-physical nodes are sustained are with long battery lives, ambient power harvesting, and solar power. They will need to minimize power consumption and make the best use of available power, especially when spread widely. Consider, in the power consumption of end-node cyber-physical devices, that network transmission is a constant power usage while active. For complicated computations difficult to run on local nodes, data can be transmitted to the cloud for it to perform the computation. However, regular and constant transmission can become a significant power consumption. The more autonomous an end node is in self-processing information, the less reliant it is on wireless transmission to the central processing system, which may be handling a large network of devices. By shifting computations closer to the end nodes, the need to regularly transmit long streams of data can be avoided, especially when there are many edge devices reporting to the same node, enabling the end node to consume less power overall. By accelerating the end device to handle computations, it is possible to avoid the majority of energy overhead of transmissions and remote server computation, making an edge node more power efficient, but placing more power consumption on the edge device during the computation. A realistic application of cyber-physical devices is predictive maintenance, a strategy for monitoring the performance of an asset to evaluate its condition and possible failure. By using cyber-physical devices to sense equipment, it is possible to reliably predict necessary maintenance through employing machine learning on the data generated and detecting anomalies outside of standard operation, thereby reducing maintenance downtimes and costs and maintaining productivity. With regards to predictive maintenance, a regularly used model architecture is the long short-term memory network, a type of recurrent network. A recurrent neural network model forms a directed graph along a temporal sequence, enabling it to accept a stream of time-step data and process it with retained state information from prior inputs. However, normal RNNs can experience the vanishing gradient, in which long-term gradients can disappear due to finite precision, preventing values from being correctly proportioned. Long short-term memory networks were developed to deal with the vanishing gradient problem by allowing gradients to flow unchanged. The LSTM avoids the vanishing gradient issue by making the model robust at the cost of increased computation. The inclusion of a cell and 3 gates better regulate information flow and retain values across intervals. The main necessary operations for processing an LSTM are multiply, accumulate, and the activation functions. For the models we examine, their structure will consist of one or more LSTM layers, with each LSTM layer generating feedback for the next layer and next time step. After the LSTM layers, a dense layer is employed to classify and return the output as either a predicted failure or standard operation per time step. As discussed earlier, edge processing for low power consumption makes sense only when the added power consumption by the edge processor is less than the resulting reduction of network power consumption. However, achieving this is not so simple because general purpose microcontrollers have low power efficiency, server scale FPGAs have good power efficiency, but require a large baseline power budget, and low power FPGAs with less than 100 milliwatts of power consumption lack the memory and processing power to host the target neural networks. We target the last scenario using model compression and other methods to deploy realistic models on low power FPGAs. Our purpose is to examine how realistic neural network models can be adapted to fit such extremely low power devices. To assist in reducing the runtime of the neural network model and fit the model onto the board's available capacity, post-training compression is an available pre-processing step to adjust the model for the neural network. One approach is pruning, selectively removing certain weights from the model to reduce the weight total. Another broader approach is quantizing, reducing the weight bit width of all the model's weights to fixed sizes, simplifying the associated operations and reducing the total necessary weight storage. The process maps a range of floating point values to a more finite set of fixed point values. For our purposes, we opted to use quantization, as accuracy can drop significantly if a pruned model is not retrained, and sometimes there is no choice in pruning availability, and pruning can also introduce sparseness. In this project, we proposed Eciton, a carefully resource and power efficiency optimized edge FPGA accelerator that runs realistic quantized LSTM predictive maintenance models on low cost, low power FPGAs. Eciton's hardware setup streams sensor data into the FPGA, which uses the LSTM model to predict failure. If detected, it informs the onboard microcontroller to transmit the necessary information to a central server that can make more nuanced, higher level decisions based on the transmitted data. To approach this extremely low power, low cost solution, we first focused on selecting the type of chip to focus our design on. The Lattice ICE40 UP5K chip was appropriate to our goals. The cost was roughly $5, making it inexpensive and good for deploying in bulk. And the chip offered full open source toolchain support through Yosis. The chip also provided a significant on-chip memory for storing a neural network model at 128 kilobytes of total single port RAM, as well as 61 kilobytes of total block RAM for computational memory and DSP blocks for compressed computation handling, though they are too small to support true floating point or wide integer operation. The DSP and SRAM resources of the ICE40 UP5K are particularly high, which made them well suited for the computational and model characteristics of LSTMs. In order to put a realistic LSTM on the UP5K chip, we first needed to compress it to fit available on-chip SRAM. Starting with the conventional 32-bit floating point from trained models, we quantized all weights and inputs into integer values, such as to 16-bit, 8-bit, and 4-bit, effectively slashing the model size by the original bit width to a new bit width ratio. We pre-established a signed fixed point range to map to from the floating point range. We also opted to keep the integers signed and centered around 0, like the original floating point range, to avoid additional 0-point offset in the quantized arithmetic computation. With the quantization of the original floating point values into fixed point signed integers, the operations to multiply and add have been modified. During arithmetic, the values are expanded to double the stored bit width for more accurate arithmetic. In order to handle the operations efficiently, given the stated signed range, we pre-calculate the scale as a proportional multiplicative coefficient, avoiding division. We avoid processing the 0 point by maintaining the signed range centered on 0. The 16-bit results are then truncated and returned as 8-bit values post-operation. Eciton is controlled through a demultiplexer that receives an activation signal from the microcontroller unit. When activated, it initiates a counter and starts to initiate a set of commands that preloads weights and sets stages into the LSTM core, and afterwards, the dense core. The LSTM core receives a stream of sensor data to the LSTM and processes each time step in series, providing feedback of the current time step to the next one. The dense core then outputs the classification for the predicted maintenance outcome, which is sent to the microcontroller to determine if it needs to report a failure or not. Eciton's LSTM core receives 8-bit input and output and produces feedback via the carry and hidden state queues. The SRAM holds 16-bit weights, carrying two 8-bit weights concatenated, which are cycled through all available weights according to the counter. The weights are paired due to the UP5K's available SRAM access, with the minimum bit width available being 16 bits. The consecutive access of the weight blocks is due to reorganizing of LSTM computations into pipelines, thus avoiding random access. Then the weights are streamed into a multiply accumulate pipeline with inputs and hidden states, cycling through all of the weights across the layers before proceeding to the next time step input. Biases are applied post-multiply accumulate. The kernel, recurrent, and bias accumulations are all combined with the current input and then processed differently according to the formulas for the gates in the state pipeline, with the hidden state queue transferring state data for the recurrent calculation and the carry state transferring data for the next carry calculation. Hidden and carry states are carried across steps and stored in on-chip DRAM buffers. TAN and sigmoid activations are replaced by hard sigmoid activations during model training, as nonlinear sigmoid activations are hard to fit on resource-constrained FPGAs, and hard sigmoid provides simpler linear computation with trained bias weights providing corrections. To evaluate Eciton, we ran two realistic, extremely low-power LSTM models on it. The turbofan model processes aircraft sensor values to predict the failure of a turbofan aircraft engine, the dataset being an engine degradation simulation. The motor model is a realistic model in which accelerometer and voltage sensor values from an electric motor are collected. This scenario has interesting real-time and energy budget requirements because the system is powered by a power harvester generating energy from the magnetic field as the motor spins, and the model processes data from the remaining time as the motor spins down. In their original configurations, neither of the above models would fit on a UP5K chip through either memory or computational resource constraints. We replaced the activations with hard sigmoid activations, retrained the model, and quantized the models across 16-bit, 8-bit, and 4-bit. While use of hard sigmoid, 16-bit, and 8-bit fixed point quantizations have gradual loss of accuracy, 4-bit quantization results in a sharp 24% drop. And while the 16-bit quantized model is sufficiently small to fit on the on-chip SPRAM, we decided on 8-bit quantization to make better use of the limited DSP blocks, performing more 8-bit operations per cycle, matching the SPRAM bit width. Eciton neatly fit onto the Lattice ICE40 UP5K chip. All 4 SPRAM blocks are utilized for the potential to store as many ways as possible. The total on-chip capacity of the 4 SPRAM blocks is 128 kilobytes, which can comfortably fit either of our trained and quantized models, and potentially much larger ones as well. The memory footprint of the turbofan model is 80 kilobytes, and the electrical motor model is 91 kilobytes. Each multiply accumulate unit requires 2 DSP blocks, so 4 DSP blocks were needed for the LSTM cell and 2 DSP blocks for the dense cell. VRAMs were used for storing states and intermediate values. Overall, the accelerator uses 94.5% of the board's logic cells while achieving a clock frequency of 17 megahertz. We compared Eciton to server machines running floating point and quantized integer computations, and to other low-cost computing units such as Raspberry Pis and Arduinos. Eciton on the ICE40 performed better than other hand-sized devices, though did not approach matching the performance of server machines. However, it had the best available power efficiency by far, operating at 2 to 5 times better than the next best device, both in comparison to other inexpensive machines and to the server machines. We also examined the performance and power efficiency comparisons against state-of-the-art sub-watt FPGA implementations of LSTMs. Despite the resource constraints of our UP5K platform, Eciton achieves competent performance and superior power efficiency with the best sub-watt performance and better performance than comparable lower power implementations. Eciton was also able to achieve the energy limit requirements of the electrical motor scenario. It took Eciton 31.3 seconds to fully process the 25 seconds of sampled data stream at a steady power consumption of 17 milliwatts by the FPGA, finishing the job within the 0.6 joule energy limit imposed by the power harvester. We looked at sustained under load total system power consumption breakdown, including network transmission for the top 2 most power efficient embedded systems evaluated, the Raspberry Pi Zero and Eciton, as well as an Arduino Nano system transmitting all data collected with no edge computing. The Raspberry Pi and Eciton systems are configured with a low-powered lower module, while the Arduino Nano is configured with a faster NB Internet of Things module due to the higher data rate required without edge filtering. We see that the power consumption of Eciton is significantly lower than other systems despite the FPGA addition. Furthermore, the power consumption is low enough that it can be sustainably powered by many proposed non-intrusive power harvesting units. In conclusion, Eciton achieved a low-cost, low-power domain for moving realistic neural network applications onto extremely low-power scenarios that have not been achieved by other FPGAs, providing competitive accuracy on 2 realistic predictive maintenance applications while satisfying stringent power efficiency limitations imposed by some scenarios. Eciton works on a 17 milliwatt power budget, costs $5 for an FPGA, has competitive accuracy, and works at the extreme edge, localizing computations near the sensor. While we have demonstrated Eciton in the domain of predictive maintenance, we also plan to explore many other cyber-physical and Internet of Things domains where such a platform can be beneficial.